Hey, this video is a follow-up to the previous one on topic 2.8, which was the least squares regression. All right. So in this video, I'm going to work through an example in which I calculate the equation of this least squares regression model here. Okay. Basically, it's just the equation of a line. Okay. Now we're going to do that with very limited information. Right. All we have to work with is the mean of the x values. So that's the foot length. As well as the standard deviation, and then the mean for the y variable, which is height, as well as the standard deviation, and then the correlation coefficient between these two variables, right? So R is about 0.7, which tells us we have a moderate to strong linear relationship between the foot length and the height. Okay, so let's start with just the general form of the equation, right? So we know in algebra 1 that a line can be represented by the form y equals mx plus b. Okay. Statisticians do it a little differently. Okay. So we don't even use y, first of all, right? We use y hat, okay? Because this line is not going to give me anybody's actual height, okay? It's going to give me some predicted heights, but it will never give me anyone's actual height. Right? Unless, say, that person's data point falls exactly on the line, right? Which is pretty rare. Okay, so we're going to use the hat symbol just to indicate that we're calculating predicted response values. Okay, all right. Now we know that lines have both an intercept and a slope. In statistics, we write it this way: a for the intercept or the constant term, plus bx for the variable or the slope term. Okay. All right, so our goal then is to figure out the values of a and b, right? If I know the slope and the intercept, then I know all the coefficients of the equation. All right, so let me make a note down here. Okay, so a is the y-intercept, and b refers to the slope. All right, so we're going to calculate the slope first. Okay. And so there's actually a very nice compact formula for determining the slope. All right, and it is the correlation coefficient multiplied by the ratio of the standard deviations, okay? So it's the standard deviation of the y variable divided by the standard deviation of the x variable, okay? So we're not gonna talk about how this formula was derived, right? It involves calculus, so that might be like a second or third year stats class, okay? But this is something that, that is provided to you on the formula sheet. So you don't even have to memorize it. It's just one of the formulas. Okay. All right, so we're just going to plug and chug now. So the correlation coefficient is 0.711. The standard deviation of the y variable is 5. And the standard deviation of the x variable is 3.45. Okay. All right, let's pull out the calculator. Okay, 0.711 times 5 divided by 3.45. All right, so we get 1.03. Okay. Right. Okay, so we have a slope that's a little bit more than 1. Okay. All right, the next step is to now find the intercept, the y-intercept. Okay. Now, something to remember about our least squares regression model, and this was in the last video, is that it will always pass through the average x value and the average y value. Okay, so we can verify that. Where's my ruler? Okay, so the mean of the foot length is 28.5, which, I mean, that's 28, that's 32, that's 30, that's 29, so maybe like about right here. Okay, and the mean of the y variable height is 67.75, right? So if that's 66, 67 would be pretty much nearby. Right. So our regression model, right, our linear model passes through the point x bar, y bar. Okay. So this is cool, right? So what we can do is we can substitute these expressions into our model, right? Replace y hat with y bar, replace x with x bar. Oh, and by the way, we know the value of b, so we can substitute that here as well, okay? And then we can just solve for a. All right, so let me just write this first, okay? So y hat equals a plus bx, and then we're gonna replace y hat and x with y bar and x bar. So we get y bar equals a plus b times x bar. Okay, so I'm not substituting any numbers just yet. I'm gonna manipulate the equation to isolate the variable a, right? So if we subtract bx bar from both sides, then we get y bar minus bx bar equals a, and then I'm just gonna change the order of those expressions. So a equals y bar minus bx bar. Okay. So this is the formula for finding the slope, and you have to find it first, okay? This always has to be the first coefficient you find because you'll need it to then find the a coefficient, okay? So this is on the formula sheet, and I want to say this one is 2. All right, so now all I've got to do is I've got to substitute the mean y value, which was 67.75, the slope, which is 1.03, and the mean x value, which is 28.50, right? And then I'll have the intercept. Okay. So this is going to equal, what did I say? 67.75 minus 1.03 times 28.5. Okay. 67.75 minus 1.03 times 28.5. Okay, so 38.395. All right. So that wasn't too bad. I mean, the only operations we're using here are addition, subtraction, multiplication, and some division. Okay, so just kind of your basic 4 operations, your arithmetic operations. All right, so now that we have the coefficients, right, the value of the slope and the intercept, we can go ahead and substitute it back here to have the actual equation now. Okay, so let's write it here. So y hat equals a, okay, so our y-intercept, okay, just over 38, 38.395, plus b, so that's going to be plus 1.03, times x. Okay. So we could leave it this way, right? Just using generic variables x and y, okay? Or we can add context, which means to replace the letters x and y with the actual names of the variables, right? So we could write the word height with a hat on it, so predicted height equals 38.395 plus 1.03 times x, which is going to be foot length. Okay, so that is how I would probably write the least squares regression equation by using the actual names of the variables instead of x and y. Okay, and it's really important that you remember to put the hat symbol here because we're not calculating anybody's actual height. Okay, we're trying to calculate some predicted heights. All right, so now, so one of our objectives was to calculate the coefficients of the regression model. Okay, so we did that here and here. Okay, another one of our objectives is to interpret what these numbers mean, right? So what do these two numbers tell us about the relationship between foot length and height. So let's kind of look at just a general graph. Okay, so this is an x-axis, and let's say we have our origin there. Okay, this is the y-axis, and then there's some regression model, some regression line. Okay. All right, so this point here represents the y-intercept of the line. Okay, so that point there has a value of a. And then the slope, we know that has to do with the rise versus the run, right? So the change in y versus the change in x, okay? So that is how we want to think of the slope, right? It's the steepness of the line. All right, let's change colors here. All right, so let's focus on the intercept first, right? So the intercept always occurs when our x variable is 0, right? When the x value is 0, that is when the line will have a value, a height of a, okay? And so that's how we want to interpret it, right? So when the x value, in this case foot length, is 0, the height will be a, which is 38.395. All right, so when foot length is 0 centimeters, the height, and I don't remember if I said this the first time, so if I didn't, I'll correct myself now. It's not the actual height, it's the predicted height. Okay, so the height is predicted to be 38.395 inches. Okay, so that is how you would interpret a y-intercept. Okay, it's the predicted y value when the x variable is 0. Okay. All right, now let's turn our attention to the slope. Okay, so the slope is, from a visual perspective, it's the steepness of the line, but from an interpretative standpoint, it's how it's the ratio of the change in y to the change in x. Okay, so we could write this as, so if the slope is b is the same as b over 1, right? So we could think of there being a b unit change in the y variable for every 1 unit change in the x variable. Okay. Right. Like I can always write any number as a fraction, right? Just put it over 1, right? So my slope is 1.03 over 1, right? So this is the change in y versus the change in x. Okay. And that's how we're going to interpret it. Okay. So we could say the height is predicted to increase by 1.03 inches whenever foot length increases by 1 centimeter. Okay, so it's the change in the y variable, height, versus the change in the x variable, foot length. Okay, so for every 1 centimeter we increase in foot length, the height is predicted to increase by 1.03 inches. And so it's important here to also include units, right? Height is being measured in inches, and foot length, for whatever reason, is being measured in some other units. Okay, so it's always important that you include units anytime you are interpreting something in statistics. All right, so here, let me give you just some general sentence frames that you can use in any situation, right? So I'll remove the context here, right, and just write a general statement. Okay. So we could say, when x is 0 units, the y is predicted to be a units. Okay. So anything that I underline, you would replace with an actual number or some actual context. Okay. When the x variable is 0 units, I probably should say x units. The y variable is predicted to be a units, and these would be the y units. All right, I'll do the same thing here. I'll remove all the numbers and all the specific contents from this statement so that we have like a general sentence frame. The y variable is predicted to increase / decrease, right? Keep in mind that it is possible for the slope to be negative, in which case, right, the y variable would be decreasing. Okay. By b units for every additional unit of x. Okay. So the y variable, such as height, is predicted to increase or decrease, so you need to look at the sign of the slope, by slope units, okay, and these would be y units, for every additional unit of x, so this would be the x units here. All right, so that was a complete worked example. So just to recap, we started with a graph, a visual, and 5 pieces of information. The means, the standard deviations of the 2 variables, and the correlation coefficient. Okay, so I introduced to you the 2 formulas for calculating the slope value and the y-intercept value. And then we talked about how to interpret those numbers. Okay, now, oh, forgot to mention, right? Does this interpretation even make sense, right? When the foot length is 0 centimeters, the height is predicted to be 38.395. Like, I don't know about you, but I've never met anybody whose foot length was 0 centimeters, no adult, right? And I haven't met any adult who was 38 inches tall, okay? So even though you can interpret any number, right, using this sentence frame, it's not always gonna make realistic sense, right? And if we look at our data, right, our data here, look at the domain, right? Or the values of the x variable, right? The smallest is about 20 or so centimeters, okay? So this interpretation would be an extrapolation, right? Because we didn't collect any data from anyone whose foot was that small. And realistically speaking, right, unless someone was an amputee, right, their foot would not be 0 centimeters long. There would be some length to their foot. Okay. So keep in mind that the y-intercept does not always have a real world interpretation, right? You can write it, but it might not make any sense at all because you might not have any data. You might not have any data where x is 0. Okay. In that case, you probably shouldn't be writing this statement at all. Okay. The slope will, I believe, always make sense, right? Because it's just talking about how one thing changes relative to the other, okay? But the intercept is specific to when x is 0, which may or may not be the case for your particular data set.